My name is Chanyoung Lee, and I'll be representing regression models for telomere length using the clinical data. Our objective is an extraction of the exact patterns or models in clinical data versus telomere lengths. So, in order to extract the appropriate patterns, we had to determine which model that we can use in order to predict the telomere length using the clinical data. We can use both. We can use either deep learnings or machine learnings. But in my case, uh, I have decided to use the machine learning models, specifically the regression models. So in order to use the machine learning models, we first have to determine the um, characteristics of our inputs, which is the clinical data. We have the clinical data as almost as 120 items or features, weight, BMI, hemoglobin, and so on. So it is very important that we know the distribution of each clinical data and determine how these patterns can how this each pattern can contribute to our models. Um, so because the each clinical data shows different patterns that is either linear or non-linear, it is important that we consider each characteristics of these patterns and incorporate into our models appropriately. Like I have previously mentioned, we have 115 features that shows uncertain distributions. As you can see here, some are normally distributed. So are some clinical data that has binary outputs has uneven distributions. Of course, uneven distributions, and some does not show the unnormal distributions, or maybe possibly the gamma distributions. So, in order to incorporate the uneven distributions of each clinical data, we have to determine theoretically the models for each the the ultimate models that can best consider the all characteristics of the clinical traits. So we have first we have to determine whether we can use the deep learning models or the machine learning models. Um, because we are using the machine learning models, then we are saying that we are using the linear relationships between independent and dependent factors. Um, and because we have only one single dependent factors, which is the telomere length, then we can use the univariate models. And since we have multiple clinical traits, then we are using the multiple. This leads us to using the multiple models. And after that, we have to determine the characteristics of our distribution of each dependent and independent factors. And you can see there are a lot of models that we can use for the regressions. So, based on specific conditions of your distribution of the data, then we can use a lot of models. Um, as for the outliers, we can use robust or quantile distributions for certain characteristics of your dependent factors. Dependent factors. Maybe such as on normal distributions or so on, then you can use GMO, survivor regression, or autoregressions based on the conditions between your dependent and independent factors. Then you can use GAN models or polynomials. Um, and then as for the multicollinearity problems, which means that the independent factors are not really independent with each other, such as BMI or level of degree of obesity and possibly the high blood pressure and so on, then we can use Lasso-Rich or PCR PLS models to tackle with those problems. And you can see there are so in here there are only 9 regression models that we can use, but in reality there are like dozens of other models that are designated in order to tackle with a specific condition of the distribution specific distribution of your data. So we are using the GAN models. We decided to use the GAN models. Um, there are actually a um, lot of characteristics for independent and dependent factors, or the relationship between those two factors that we can. So in reality, we had to use a lot of models to describe the characteristics of each data, but since we are using only one models, we decided to choose the GAN models that describes the non-linear relationships between the dependent and the independent factors. So the GAN models attempts to add up all the independent factors that has non-relationships between the dependent factors. Theoretically, linear relationship equations should be illustrated like this. So you can see that all independent factors, which is described as the x, has the coefficient next to each other's. So all linear relationships should be described as is here. But since we had all the clinical traits that have uneven distributions for each data, then we can assume that they have some clinical traits does not have the exact linear relationships to independent factors. That's why we decided to use the GAN models to describe the non-linear function as well. So if you look into this, you can see this is described as a functions that transforms the relationships of dependent factors into that describes the transformation of independent factor to the dependent factors. So linear model is illustrated in terms of non-linear function that creates the spline in each section to create many small linear relationships and combine this. So what they're saying is that we have this somewhat polynomial or non-linear relationships here, and then you can see that data is somewhat so you have this like linear relationships here. So what they're doing with this data is that they're creating this the spline here and here, here and here, and then they are drawing the linear relationship between here and here and here and here, and they try to smooth the line like this ones, and so on, in order to create in order to describe the non-linear relationships between the dependent and independent factors. This is the distribution of the term limit length. You can see that it doesn't have the normal distribution, but these are the top 5 models that can best describe the data. You can see the gamma model is the most familiar regression models. This is the distribution of each clinical traits. You can see that some traits are not some traits are not evenly distributed. They have gamma, some have gamma distribution, some has exponential distribution, some has chi-square, and so on. And some has normal distribution as a result. So this is the result of fitting model, fitting gun model for all clinical traits and telomere length. You can see that there are dozens of um, the scales that can show you the fitness of your model to the data, showing you the error rates. I'll describe the error rates after the the pre-processing of data has been finished. So the significant code shows you the contribution of each data or each clinical traits to the models, showing you how significant this clinical trait it is. The p-value is p-value, as you know. The lambda model, the lambda value shows you how the smooth the line should be, as I previously mentioned in previous slides. And S0 to S whatever it is, the index of the clinical trait. So we actually want to see the contribution of each clinical, or the power of each clinical trait to the telomere length, since we are combining all of the scores of each clinical traits. This is called as partial dependence plot. You can see that like the value of the clinical traits. So the best patterns that the clinical traits can show you is either the value its value is starting at the top and decreasing all the way through, or the opposite way. But so the worst scenario for the partial dependence plot for each clinical trait is the fluctuation of the values. You can see there are specific fluctuation at the first section of the graph, and it's kind of smoothing all the way around. So you have to put more spline, or you have to place more knots in order to smooth the line here. So you can see there is more fluctuations here, here and here, and here. So you have to somewhat change the parameters of values in order to smooth these lines, and somewhat draw the somewhat make the linear lines, so we can see more exact patterns. So when you draw the splines here, then you can place the knots here and here, and you have dots that kind of makes an intersection between the graph and the nodes. And then after this, you can smooth a line like this, and like kind of draw the maybe smooth line among the fluctuations. So when you have the linear relationships after smoothing the lines, then you can see more exact patterns and see how each clinical trace can be determinant for the telomere length. And this is another partial dependence examples too. The first patterns for BMI is the worst scenario that you can have. It has a lot of fluctuations, and the values between at the start and the bottom, at the starting point and end point does not have much difference, even if you place the notes maybe around here, then like kind of the intersection will not be changing a lot. So when you place the smooth line here, it will go just like this ones. So the horizontal lines are the worst case, that you cannot describe you cannot determine whether the clinical trait is determinant or non-determinant. But anyway, in order to reduce the fluctuation as many as possible, you have to draw the spline or knot in order to smooth fluctuation or get more exact patterns or regression line for each clinical trait. By doing this, we will show you more patterns of contributions for each specific section of each clinical trial analysis. Thanks for listening.